Now I'm going to go over using a normal distribution for selecting our weights. So again, TensorFlow provides this function tf.randomNormal for us. What this does is it selects random numbers from a normal distribution. And again, we give it the shape and parameters like the mean and standard deviation, and then it'll just grab these numbers for us. And we can use these random numbers to initialize our weights. So here's what a normal distribution looks like. Again, we're using histograms, so we've binned our values. So again, select 1,000 values from a normal distribution and use the histogram to actually view this distribution of our numbers. So you can see that you get this tail, but most of the values are centered around 0 here. Then let's compare the normal distribution against our previous runs with a uniform distribution. Here again, we're looking at the loss over training batches. And this time red is our uniform distribution, which we found before. So in a range from -0.1 to 0.1. And then blue is initializing our weights with a normal distribution where the standard deviation is 0.1. So you can see that this is actually lower. The loss is lower for the normal distribution pretty much at every point in training. And just a little bit lower, but it is lower. And there are some places where the normal distribution is doing worse. But in general, in aggregate, if you look at all these numbers, then on average, the normal distributions can be doing better. And you can see, looking at the validation accuracy and the loss, that using the normal distribution to initialize our weights is just slightly better. Again, this might be due to some random variations, but overall, if you did this a whole bunch of times, you would find that the normal distribution usually does better than a random uniform. Okay, so as you see up here, with a normal distribution, you actually still get some fairly large numbers that are in these tails. So, and these can, setting your weights to these large numbers can be detrimental to training your network. So what we'd prefer is if we could pull these numbers closer to 0. So what we can do is just say let's just not sample anything from somewhat past a threshold. So you can say our threshold is -2, +2, so we're just not going to produce any numbers outside of this range between -2 and 2. But it's still going to be normally distributed so that we get most of our values around 0. And this kind of distribution is called a truncated normal distribution. So it's truncated because you're cutting off the tails here. Again, TensorFlow provides this for us, so truncated normal. You can use this function to initialize your weights using a truncated normal distribution. So what this does is it generates numbers from a normal distribution, except where the values have a magnitude that is more than 2 standard deviations from the mean. So that in this case, if your mean is 0 and your standard deviation is 1, so any value that has, or any random sample that the value is greater than 2 will just be discarded. And then we'll repick it, resample it from the normal distribution. And we can see what that looks like here. So you can see that, again, we have this normal distribution centered at 0, but we don't get any large values. And again, we can compare this truncated normal distribution to the normal distribution. So in this plot, our normal distribution is red and our truncated normal is blue. And we can basically see that there's no difference. And if you look at the validation accuracy and loss, again, they're really, really similar, really close. So there's basically no difference between the two. However, this is mostly because the network that we're using is pretty small. We only have 10 input classes. We're only using 256 units in our first hidden layer. So the deal is if you have a larger network with a bunch more weights, then you're more likely to get these extreme values in your normal distribution. So for a small network, it doesn't really matter if we're using normal or truncated, but we're using large networks with a whole bunch of weights. It's usually better to use a truncated normal so that you don't get a lot of these really large values being sampled from a normal distribution. Okay, and so finally we can compare where we started, which is using a random uniform distribution from 0 to 1 as compared to our truncated normal distribution. So again, this truncated normal distribution does so well that we can't even see the loss on the scale of our baseline. And we went from about 66% accuracy to 97% just by changing the way we initialized our weights. So you can see it's really important to do this correctly if you want to get the best performance out of your network. All right, I hope this was helpful and that going forward, you'll be able to understand how to initialize your weights in the best way possible. Cheers.